So, Kepler's laws, that is what we are going to discuss now. But before that, as I have discussed already, I have told you already, we will look into the history of astronomy in mid 14th and 15th and 16th century. So, the famous apple that fell on Sir Isaac Newton's head was somewhere in 1966, when Newton was a 24 years old student of mechanics in Cambridge University. But before this, there is a history of almost 200 years. Nicholas Copernicus, born in 1473, was the first of these modern day astronomers, who came up with the first realistic model of solar system with sun at its center. Now, of course, this model was this model was far from being right. He tried out many different things, which eventually he eventually came up with this model based on his observation of the stellar system. And please remember that this was the time before Galileo. Galileo came almost 100 years after him, or more than 100 years after him. Okay. And Galileo was the first to develop something like a telescope. Most likely there was a story that Galileo was not the first who discovered telescope, but he was the first to discover, to apply it in case for observation of the stellar system, observation of stars and moons and their motion. So, all the modern day, all the olden days astronomy, that was half observation and half myth. There was no very solid account of very solid physics, or rather solid knowledge why the motion takes place in certain manner. And there were lots of myths about stars, myths about movement of celestial systems, myths about how it can affect the fortune of one, fortune of a nation, fortune of the king. So, many of the eminent astrophysicists, as we could call them now in modern days, were associated with the royal court. They were the royal astrologer of some king, who has to suggest the king whether this is a good time to go for go for a you can go for a war, or is it a good time to to make a move in politics, things like that. Now, and there was a heavy influence of church in it. So, in Europe, especially the Roman Catholic Church, they used to have a huge influence on this astrological observations. Okay. And according to church's belief, earth remains at the center of this universe. Everything evolves around the earth. So, it was also a very intuitive knowledge sitting on that day, because we all see that the sun comes up every morning in the east and goes down in the west. Moon comes up occasionally on the sky and goes down once again. So, it's why, of course, it is true that earth is stationary and every other stellar objects are evolving around earth. But please remember, although they were as naked eye astronomers, they used to observe things very closely. Okay. So, before Copernicus also there were Ptolemy and other astronomers, and there were of course contribution from Indian astronomers and Arabic astronomers, who had created a map of the stars we could see with our naked eye, and they could identify a few planets as well. Okay. Now, these were all tabulated. The tabulation was nice, tabulation was accurate, and based on their tabulation and based on the observation, again there is a history behind it. Not that Nicholas Copernicus in one single day came up with the idea that instead of earth, sun is at the center of the solar system. It is not like that. So, he also went through all the available knowledge, and he thought, being a logical person, he thought, okay, maybe church is wrong, maybe It is not the earth which is at the center of the system, but it is the sun which is at the center of the system. So, he came up with this new model. Of course, this model was not acclaimed heavily by church, it was scrapped. Okay. But because Nicolaus Copernicus, he was also a clever man. You have to be a clever man if you are, if you want to challenge a notion which was there for centuries and which is directly backed by the Roman Catholic Church. So, he did not make much noise about it, but his contemporary astronomer Galileo Galilei, who discovered telescope, well, he did not. There is a controversy related to that, but he used it. At least he was the first one to use it to observe our solar system. So, in a sense, he experimentally verified the theory which Nicolaus Copernicus came up with, that it is not the sun which not the earth which sits at the center of this universe or our solar system at least, but it is the sun which sits at the center of the solar system. So, we probably all know the story that Galileo Galilei was under immense pressure from the church, and after few years he was confined in his house arrest almost. He had to also suffer time in jail. So, he was under pressure to change his statement. So, eventually he had to obey to what the church said, and he had to retreat. He has to retract his statement that earth is not at the center of this universe. Anyway, but all good work essentially pays off. So, after almost 100 years of his death, or more than 100 years of his death, it was the first time when Roman Catholic Church officially agreed that okay, Galileo was, it was not a justified move to put pressure on Galileo and make him withdraw his statement. And in 1992, as late as 1992, Pope John Paul II officially expressed what you call. So, he officially condemned the move what church made in order to stop Galileo from publishing his results, and Pope Benedict II in 2016 he declared Galileo, he accepted Galileo's contribution in astronomy and modern day astronomy, and he considered him as one of the assets of the society. So, as we see, all good work sooner or later it pays off. Now, what happens after Galileo? Galileo's time is almost like, okay, he has some overlap, he did not have any overlap with Copernicus, but at the same time there were two other very famous astronomers of their time. One is this Danish gentleman named Tycho Brahe, who was last of the naked eye astronomers. He did not believe in this telescopic concept. He did it in the so called traditional way. He started observing stars and their movements with the help of the naked eye, but he maintained a very nice account of the thing. Extremely well documented movement of stars and planets and moons were found in his record. Now, Jonas Kepler, he was a German by birth. So, by the way, Tycho Brahe, although he was a Danish scientist, Danish nobleman essentially, he moved to Prague, and that time Prague was the capital of the almost the intellectual capital of Europe. So, all the big names in literature, in history, in mathematics, they all went, they tried to went to Prague. That was their final destination. So, that is where Kepler and Tycho Brahe met essentially. So, Tycho Brahe had his own observatory which was some distance, which was set up at some distance from Prague, and Kepler went there as an apprentice to work with it. So, very soon he found out there is a lot of potential in the data which Tycho Brahe had. By the way, Tycho Brahe also had his own model of the universe or the solar system, which in a sense was almost right. He said, okay, sun remains at the center of the solar system with all other planets evolving around sun, but Earth stays outside and the whole thing moves around Earth. So, he again once again he did not want to go directly against the church, but what he did was he was trying to make a bridge between the philosophy and science or religion or science without antagonizing both of the sides. Okay. So, anyway, so his contribution, his main contribution to this movement towards gravitational theory of Newton was that his documentation. He was very good with his documentation power. And then came Jonas Kepler sometime in mid or early 1600. He essentially gathered gathered all the information he could find from the work of Tycho Brahe and Galileo, and of course Copernicus. Copernicus was the first to propose this model and tried to combine them in 3 laws, and then he came up with the Kepler's laws, famous Kepler's laws of planetary motion. What are these laws? We will see in a moment. Okay. So, let us look at into the Kepler's 3 laws, okay, one by one. First law is movement or path. That time orbit, the term orbit was not coined, but let us use orbit because we will be using this term a lot. Orbit of each planet is an ellipse with Sun at one of the foci. Ellipse has 2 foci, so 2 focal points. Sun has to be at one of them. So, it is called Sun at one of the foci. Okay. So, this is the first law. Second law is the line, or rather I will instead of, so you can find the statements anywhere. So, instead of writing them on board, what we are going to do is I am just going to give you a brief picture. So, what he said was, if this is the orbit of a planet, it has to be an ellipse with Sun at one of its center. That is the first law, one of his foci. Second law, the line that joins the planet to the Sun sweeps out equal area in equal interval of time. So, let us say if it is at time t1 it is here and time t2 it is here. If this is the area, if the swapped area, the checked out area is A, then and in another time t3 and t4, this area is, let us say this one is A1 and this one is A2, then his second law was A1 divided by T2 minus T1 is equal to A2 divided by T4 minus T3. So, the thing is moving in this direction. So, T4 is greater than T3 and T2 is greater than T1. So, it sweeps out equal area in equal interval of time. So, that means aerial velocity is constant. So, that is the second law. Now, the statement of the third law is a bit tricky. If the planet has a time period of t, time period means if it starts from this particular point, it evolves around the sun and comes back to the same point in time t, then this time t has a relation with the length of semi-major axis of the ellipse. Now, we all know that ellipse has two axes, one semi-major and one major axis and one minor axis. So, the length of this major axis is taken as 2a, whereas that of the minor axis is taken as 2b. So, this semi-major axis is this length essentially. Okay. So, the statement of this law was t square is proportional to a cubed. So, length of the semi-major axis is proportional to the cube root of cube root of the length of the semi-major axis is proportional to the square of the time period. So, that is the third law. So, first law says it is an ellipse, second law says the aerial velocity is constant, and third law says this. Okay. Now, please remember that these three laws were purely observational at that time. He observed things, he relied not only on his observation, but the observation his predecessors has made, his contemporary other scientists like Tycho Brahe has made. He analyzed all this data and he came up with three laws, which later on was proved by Sir Isaac Newton. Now, what happened is, now it might be a coincidence, but if you look back, Galileo Galilei died in 1642. Same year, Sir Isaac Newton was born, of course in a different country. Galileo was from Italy and Sir Isaac Newton is from Britain, Great Britain. He was born, and probably we cannot really summarize the contribution of Sir Isaac Newton in one slide, in one page of a presentation. It is not possible, because he is the man who developed modern calculus. He is the man who worked out fundamental properties of light. We all know that experiment of Newton ring we perform even today in our laboratory. Okay. He established the laws of motion. We all know that Newtonian laws of motion, first law, second law, third law, which is still, which basically, is the fundamental of modern day mechanics. And also he developed the theory of gravitation based on which was the one of the prime motivation for that was this three Kepler's laws. Okay. Anyway, so that can wait later. How this happened and how this development was particularly made, that we cannot go in details of this in this particular class, but what we can do essentially, we can try to prove the three Kepler's laws, okay, first law, second law, third law, assuming that the force between the sun and a planet is of this nature. Now, this is the contribution of Sir Isaac Newton. K, we all know that this law exactly is f of r is m1 m2 by r square. We all know that. And this law came more than 100 years later of this, after this law, after this Kepler's law, Kepler's first law, second law and third law. Okay. But it turned out that these laws were developed keeping in mind the observation which Kepler had and based on which Kepler came with these three laws. So, Newton was a student in Cambridge and he was a student of mechanics to begin with. And then by the time he is a as far as I understand, he was a self-taught mathematician. He first derived the calculus, modern day calculus. He started working on, he started reading the works of previous pathfinding astronomers like Copernicus and Tycho Brahe. He was going through their journals, and at that time he realized then he realized that there must be some kind of an universal law which actually essentially making this basically which drives this whole universe, and that is when the apple fall. Then he realized that the pull, the force which makes the apple coming down from a tree is the same force which makes the moon evolves around the earth, and is the same force that makes the earth to evolve around sun. And also he came up with a very important concept which we will be discussing very soon, that see it is a two body problem. So, the if you look into his relation, the force is proportional to m1, m2 and r square. Now, for this entire discussion so far, we are assuming that the force center is a stationary object. We have never discussed about the motion of this force center. He also came up with the idea that it is not, nothing is stationary in this world. So, even if sun is very heavy and earth is very small compared to sun, the sun on earth is as equal to the equivalent opposite to the force of that earth extends on sun. So, if earth is moving, then sun is also moving. So, it is not the distance r, what he realized is not exactly the distance that joins the two masses, but it is the motion, it is the locus, I mean sorry, it should not be measured from setting origin on one particular mass, but we have to set the origin to a point which does not move with respect to both of these mass. Then came the concept of center of mass. So, that way he is also the pioneer of modern day rigid body dynamics, which deals with the center of mass of a body. And we will see later in this course, I mean in the scope of discussion on central forces itself, that this r is strictly speaking is not the position vector that joins these two lines taking the origin on this particular fixed mass. There is nothing called a fixed mass. It is basically the origin at which the center of mass lies. We will do that in a moment. But now, let us try to use this particular force law and try to derive three, or try to prove three Kepler's laws. Okay. To prove the first law, we do not have to do much, because we have already seen that under the action of inverse square law of force, the closed orbit, I mean only possible orbits are circle, ellipse, parabola and hyperbola, and out of those only circle and ellipse are closed orbit. Okay. Now, again when we will be going slightly advanced into this, we will see that circle is a very special case of ellipse. Ellipse is the most general case of a closed orbit. So, the first law which says the motion of a planet around sun is an ellipse with sun at one of the sun at one of the foci is correct. So, this law is immediately verified, because we have a inverse square force law acting between these two, and the only closed orbit in an inverse square force law is a ellipse. Circle is a very special case of ellipse, that we will see later. So, first law is immediately verified. Second law says it sweeps out equal area in equal interval of time. Now, in terms of calculus, this law essentially means, so the first law is ellipse, which we immediately verify. Second law is dA dt equal to constant. Sweeping out equal area in equal interval of time essentially means that in words of calculus, aerial velocity is constant. That means it is equivalent of saying dA dt is equal to constant, A being this area. Now, let us try to elaborate this. I am just taking a segment of any conic section, okay, or any orbit which is traced out under the action of a central force. Let us say this is my r and this is my dr, which is r d theta, and this is my d theta. So, the area is half into r d theta. So, dA is equal to half into r d theta, which is nothing but half r square d theta. So, if we now try to find out the areal velocity in differential form, we immediately see that dA dt is d theta dt equal to half r square theta dot. And what is r square theta dot? R square theta dot for any central orbit does not matter if it is an inverse square law or not. R square theta dot is a constant which is given by L by m. Okay. So, we immediately see that dA dt is L by twice m, L by twice m, which is a constant. Okay. Now comes the third law, and the statement of third law is T square proportional to A cubed. How do we define T? T is the areal, T is the time period which could also be equal to areal velocity. Okay. Anyway, so it will take little longer to derive this equation, and we also have to use this equation in part. So, we will just keep it for the next class, but for now what we see is we have already verified 2 laws out of the 3 laws, taking force F of r to be minus 1 by r square, or rather m1 m2 by r square. Minus sign comes because of there is a this and r cap. So, minus sign comes because these are gravitational force is attractive force. It will also be equally applicable for electrostatic attraction or electrostatic repulsion. So, for electrostatic attraction or repulsion, the path of a charged particle will be a conic section. Okay. Now, what is important is the first law is valid only for this particular force law, whereas the second law is universal for any FR. Any central force will have dA dt equal to L by 2m, which is equal to a constant. Okay. So, out of 3 Newton's, out of 3 laws of Kepler, he did not know that he found out some law which will be universal to all central orbit, and without surprise that is also followed by our planetary, the solar system. Okay. So, with this we stop here today, this particular class, and in the next class we will start deriving this particular equation. Thank you.